Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Lesson 34, Equilibrium Constants, Part 2. We should learn how to calculate Kp, Kc, or the quantities of species present at equilibrium, define and determine the degree of dissociation alpha, and deduce the expression for reaction quotient Q, and predict the direction of net reaction by comparing the values of Q and K at equilibrium. The problems and calculations of Kc and Kp can be divided into two types. The first one is you are given the equilibrium quantities, for example, the concentrations and partial pressure, so that we can calculate and solve for Kc or Kp. The second type is we are given the initial quantities, so that we have to use the ICE table to solve for the equilibrium quantities. This is a bit challenging. Let's do example 6.9. The following equilibrium process has been studied at 230 degrees Celsius. 2NO plus O2 becomes 2NO2. In one experiment, the concentration of the reactant species at equilibrium are found to be, as mentioned in the question. So calculate the equilibrium constant Kc of the reaction at this temperature. Let's write this down in your page 171. The Kc expression is concentration of NO2 to the power of 2 divided by concentration of NO to the power of 2 times concentration of O2. This gives you 1 mark. Equals to 15.5 to the power of 2 divided by 0.0542 to the power of 2 times 0.127. All these three values are given in the question, and you have to substitute it with the concentration of each species from the balance equation. And you got the final answer, 6.44 times 10 to the power of 5 per molar. Question number 2. The equilibrium constant Kp for the reaction 2NO2 becomes 2NO plus O2 is 158 at 1000 Kelvin. What is the equilibrium pressure of O2 if the pressure of NO2 is 0.4 atm and the pressure of NO is 0.27 atm? Firstly, we need to write the Kp expression for the balance equation. So Kp equals to the partial pressure of NO to the power of 2 times partial pressure of O2 multiplied by the reactant partial pressure of NO2 to the power of 2. We want to find the partial pressure of O2. So we arrange partial pressure of O2 to become the subject and substitute all the values given in the question. 158 is the Kp constant times 0.4 to the power of 2 and divide all of them with 0.27 to the power of 2. The answer is 346.8 atm. Please do all the 5 questions in practice 6.4 so that we can discuss it in the Telegram group later. Now we're going to look at how to use the ICE table. I stands for initial, C for change, and E for equilibrium. The first step is we have to express the equilibrium concentrations of all species in terms of the initial concentrations and a single unknown x, which represents the change in concentration. Then we write the equilibrium constant expression in terms of equilibrium concentrations. By knowing the value of the equilibrium constant, we can solve for x. Having solved for X, we can calculate the equilibrium concentrations of all species. Let's do example 6.10, question number 1. A mixture of hydrogen gas and iodine was prepared by placing 0.2 mole of H2 and 0.2 mole of I2 into a 2-liter flask. After a period of time, the equilibrium was established, and at equilibrium, the concentration of I2 had dropped to 0.02 molar. What is the value of Kc for this reaction at this temperature? Okay, the first thing that you need to do is write the balance equation on top, and then you are going to write initial in the first row so that we can calculate the concentration of the reactants by using the number of mole given in the question divided by the volume of the flask used. For hydrogen gas, it's 0.2 over 2. We got 0.1 molar. And for iodine gas, it's also the same, 0.1 molar. At the beginning here, there is no product formed, so we put 0 on the column for product, Hi. The next row we're going to write on the change in concentration, and after that we're going to find the equilibrium for each species. This is what we call I's table. What is X? X is the amount of reactant that becomes product, and we don't know X. X is an unknown. So for I2, it's going to be X also. It's negative because we minus X from the original initial concentration of the reactants. And for product, we're going to have plus 2x. 2 is the stoichiometric coefficient from the balance equation. Next, we're going to do the equilibrium concentration. So now we write 0.1, the initial, minus change, minus x, the same as I2. And for product, we have 0 plus 2x. Now, let's solve this. The question also gives that the equilibrium concentration of I2 is 0.02 molar. Here we can find X. X is 0.08. When we got X, we can find the concentration of H2, which is 0.02, and Hi, which is 2x. So 2 times 0.08 is 0.16 molar. We have calculated the equilibrium concentration for each species in this equation. So the next part is we're going to write the Kc expression, 1 mark, and then we're going to substitute all the values inside the expression. 0.16 to the power of 2 divided by 0.02 times 0.02. The answer is 64. There is no unit. Question 2. The atmospheric oxidation of nitric oxide 2NO plus O2 becomes 2NO2 was studied at 184 degrees Celsius with pressure of 1 atm for NO and 1 atm for O2. At equilibrium, the partial pressure of O2 is 0.506 atm. Calculate Kp. First step is writing down the balance equation. 2NO plus O2 becomes 2NO2. Then we write the initial pressure for each gas given by the question, which is 1 atm for each of the reactant, and at the moment there is no pressure for the product yet. Then we write the change by using X. So according to the stoichiometric coefficient of the balance equation, for NO it is minus 2x, for O2 it is minus x, and for product it is plus 2x. And what is the equilibrium pressure? For NO it is 1 minus 2x, for O2 it is 1 minus x, and for the product 0 plus 2x, making it 2x. Now, in the question, it is given that the partial pressure of oxygen gas is 0.506 atm. So we can find X. 1 minus 0.506 is 0.494. In that case, we're going to use this X to find the partial pressure of NO. So 1 minus 2x, we substitute x, we got 0.012 atm. The partial pressure of O2 is given in the question. And now we find the partial pressure of NO2, which is 2x, 0.988 atm. Finally, we list down all the equilibrium partial pressures of each species in the balance equation, and then we write the Kp expression, which is partial pressure of NO2 to the power of 2 divided by the partial pressure of NO to the power of 2 multiplied by partial pressure of O2, and we substitute the partial pressure of NO2 is 0.988 to the power of 2 divided by 0.012 to the power of 2 times 0.506, and the answer is 1.34 times 10 to the power of 4. Question 3. At certain temperature, the equilibrium constant Kc for the reaction Br2 becomes 2Br is 1.1 times 10 to the power of negative 3. The initial concentrations of Br2 is 0.063 molar and Br is 0.012 molar. Calculate the concentrations of these species at equilibrium. Let's do the ice table immediately. X is the change in concentration of Br2. So the initial concentration is 0.063 and 0.012 respectively for the reactant and products. The change is negative x, positive 2x, because it depends on the stoichiometric coefficient of the balance equation. And the equilibrium concentration is 0.063 minus x for Br2 and 0.012 plus 2x for Br. How are we going to get the equilibrium concentration for each species? First, we need to find the Kc expression. So, concentration of Br to the power of 2 divided by concentration of Br2. And then we substitute the values that has x in it inside the expression. So 0.012 plus 2x to the power of 2. Here we're going to use quadratic equation divided by 0.063 minus x. This is equals to 1.1 times 10 to the power of negative 3. How do we solve for x? Well, we are going to get a quadratic equation out of this. So Since 1.1 times 10 to the power of negative 3 is given, here is the quadratic equation that we're going to have. This is a simplification of it. And you have ax squared plus b squared plus c equals to 0. We insert into this formula, or you can just use it directly from your calculator. We're going to get two values of x. Both is a negative value. Which one is going to be used? Now, how are we going to determine chemically meaningful x values? So here is again our ice table. We're going to use the formula at equilibrium concentration for each species. And the first x is negative 0.0105. Substitute into the equilibrium concentration, we got 0.0705 and negative 0.009. We can't have a negative concentration. So this is not right. Therefore, we cannot use this x. The second x is negative 0.00178. We substitute into BR2. We got 0.0648 and 0.00844 for BR. This is the correct x value. Only one x value makes sense chemically. So we're going to use x, the second, and we got the concentration of BR 0.00844 molar and BR2 0.0648 molar. This is the final answer at last. Please do the 5 questions of practice 6.5 later. Now we look at the degree of dissociation alpha. What does dissociation reaction means? It means a molecule is broken down into smaller molecules, atoms or ions. The fraction or the percentage of the molecules that dissociate is called degree of dissociation alpha. Alpha can be 1 or 100% if complete dissociation occurs. So the formula to find the percentage of alpha is the change in concentration divided by the initial concentration multiplied by 100%. A reversible reaction for thermal dissociation is brought about by the application of heat. When cooled, the products bond again to give the original compound. Example 6.11 is showing us how PCl5, N2O4, and ammonium chloride dissociates. Please write this down in your page 176. Let's do example 6.12, question 1. The concentration of hydrogen ion measured for methanoic acid 0.5 molar is 8.9 times 10 to the power of negative 3 molar. Write the chemical equation for the dissociation of methanoic acid and find the degree of dissociation of the compound. The first step that we are going to do is write the balance equation on top, and then we are going to find the concentration for initial of methanoic acid, 0.5 molars. Given in the question is the concentration of H+. So we can immediately write the changes of H+. Here, 8.9 times 10 to the power of negative 3. It's the same as HCOO minus, and it's going to be negative for the product. What happened is we're going to get the equilibrium concentration when we deduct the 8.9 times 10 to the power of negative 3 from the initial concentration 0.5, we're going to get 0.4911. Alpha is the change in concentration divided by the initial concentration. So we have 8.9 times 10 to the power of negative 3 divided by 0.5. The answer is 0.0178 or 1.78%. Question 2. At 180 m and 28 degrees Celsius, PCl5 is 25% dissociated, or it has the alpha 0.25. The products of the dissociation reactions are gases PCl3 and Cl2. Write the chemical equation for the dissociation and calculate the Kp. How to answer this question? First, as usual, we write the balance equation on top to start the ice table. The initial concentration of the reactant PCl5 is 1 or 100 because it is not decomposed yet. PCl3 and Cl2 is 0 respectively. Then we use the changes X or alpha given in the question. If we use 100, it's going to be 25, but we use 1, so the alpha is 0.25. So it is negative X or negative alpha for the reactant PCl5. So it becomes 0.75 for the equilibrium concentration. And positive alpha becomes 0.25 and Cl2 is 0.25 as well. So we are going to add in all the number of mole at equilibrium for each species. So 0.75 plus 0.25 plus 0.25. The total is 1.25 mole. Why do we do this? Because we want to use Dalton's law. Dalton's law states that we can find the partial pressure of the gas if we know the mole fraction and the total gas pressure. So the partial pressure of Cl2 and PCl3 is 0.25 mole divided by 1.25 multiplied by 1 atm. This is 0.2 atm. And the partial pressure of PCl5 is 0.75 divided by 1.25 multiplied by 1 is 0.6 atm. Next, we find the expression for Kp and insert all the partial pressure that we have calculated, and the final answer is 0.0667 atm. Alhamdulillah. Please do practice 6.6, the two questions, in order to evaluate whether you understand the topic on degree of dissociation or not. The next part is predicting the direction of a reaction. In order to predict the direction, we compare Kc or Kp with the value of reaction quotient, Qc or Qp. The expression for Q is the same as equilibrium constant K. The difference is that Q is determined from non-equilibrium conditions. By comparing the value of Q with K, it's possible to decide the direction of the system. If you calculate the Q is larger than K, in order to reach equilibrium, the system will proceed from right to left. If the Q is equals to K, the system is already at equilibrium. If the Q is less than K, the system will proceed from left to right. Let's do example 6.13. At 375 degrees Celsius, the initial concentrations of N2, H2, and NH3 are 0.0711 molar, 9.17 times 10 to the power of negative 3 molar, and 1.83 times 10 to the power of negative 4 molar respectively. If the equilibrium constant Kc for the reaction is 1.2 at this temperature, decide whether the system is at equilibrium. If it's not, predict which way will the reaction proceed. Here is the balance equation. So let's calculate the QC. The expression is the same as Kc. So the concentration of ammonia to the power of 2 is 1.83 times 10 to the power of negative 4 to the power of 2. Divided by the concentration of N2, 0.0711 times the concentration of H2 to the power of 3, 9.17 times 10 to the power of negative 3 to the power of 3. The answer is 0.611 molar to the power of negative 2. This value is less than Kc, meaning the system is not at equilibrium. The net result will be an increase in the concentration of ammonia and a decrease in the concentration of nitrogen and hydrogen. The net reaction will proceed from left to right until equilibrium is reached. Please do practice 6.7. And thank you very much for watching. We will see you again soon enough, inshallah. Assalamualaikum warahmatullahi wabarakatuh.